Okay, let's go ahead with more properties of Bessel function. Every second order differential equation should have two linearly independent solutions which can be obtained from the initial equation. In this case, we have a very simple solution to initial equations. M takes a value of plus or minus nu. So these two forms the linearly independent solutions of Bessel equation. However, there is a minor problem here that when the nu takes the integral value, that is 1, 2, 3, 4, etc. So minus Jm and plus Jm are related to each other. That relation can be obtained from the solution which we have already got. The relation is given by this equation for the integral values. If they are non-integral values, then these two cannot be related and they form a set of linearly independent solutions. So one can use them as a linear combination to form any solutions. However, this relation makes it problematic, and one often uses a function named Neumann function instead of j minus nu. It is defined in terms of j nu and j minus nu with the following relation. So it's easy to see that this relation is not defined for the integral values of nu. So that is it breaks down. However, an interesting thing to note that these Neumann function can be defined as a limiting case of nu going to be integral, and they can be defined as a limiting case. With this, that instead of using j nu minus nu and j plus nu, one can use j nu and the Neumann function as a set of linearly independent solution to get as a linear combination to get any general solution to the differential equation. Let's look at the plot of Neumann equation. We have used power series solution at the regular singular point at x is equal to 0. Since x is equal to 0 is the regular singular point, it can be shown that only one of the solution is well defined and the other solution is going to blow up. We have seen that the Jm at x is equal to 0 are well defined. J0 actually takes the value of 1 and the rest of the Jm takes the value of 0. So it is clear that the Neumann function at x is equal to 0 will blow up. So that is one of the outcome of this differential equation. Let's look at the plot of this Neumann function for different values of integral values of n, and you can see them, they all blow up very close to x is equal to 0, and then they will slowly oscillate around 0 with a reducing amplitude in the similar fashion as a Bessel function. One can use both of these to solve the boundary value problem. However, one should be careful. If your domain contains 0, then you cannot use Neumann function, while you can use the Bessel Jm. If your domain does not contain x is equal to 0, then you can use both Bessel and Neumann to in your boundary value problems and then obtain the appropriate solutions. So there is another concept of asymptotic expansion. We have seen that when x is very large, the system, the behavior. Uh, However, you should know that when x is equal to infinity, the point is an irregular singular point, and we may not have a proper solution or solution necessarily blow up. But one may take a asymptotic expansion, do a various approximation to obtain the solution to the Bessel function, for very large x, and this can be done by approximating the Bessel ODE itself. One may ignore certain terms for the higher value terms and then solve the differential equation. One of the interesting asymptotic expansion is retaining the or ignoring all the value of x square or larger because they diverge very quickly. So you take very small value of x and solve, and you solve this equation, then you would get two solutions in terms of cos and sine. Of course, it is not completely cos and sine. There is a 1 by x which is prominent, and this solution would go to 0 when x goes to very large solution. One can see that the solution behaves as a combination. One can see that these solutions are behaving like sine and cos. This gives us a new idea to produce another combination of Bessel function, which is called the Hankel function. It's very similar to where we define the sine and cos or exponential function because sometimes sine and cos are useful, sometimes exponential functions are useful. Similarly, using Bessel and Neumann function, we can define what is known as a Hankel function, which are defined with the following value. Now, see that the Neumann functions are linearly independent to the partial these equation, and one may choose one of these equation based on the various domain we use. In short, solution to Bessel equation, currently we have various combinations. One is a Bessel function with the nu and minus nu. Sometimes those combinations are useful. Sometimes Bessel and Neumann functions are useful, and sometimes you can use Hankel function 1 and 2. One has to make a judicious choice of which solution to use. But however, this idea is very common in terms of the harmonic function too. We can use sin x, cos x, or e power I theta, or e power ix, or e power minus ix. With the similar idea, we have a Bessel, Neumann, and Hankel function